We welcome the leadership of Limbus AI. Hi, guys.
Hey,
Hey,
Ben.
Ben.
Happy Friday.
Yeah, likewise.
I want to start off, let everyone get to know you guys a little bit so you can pick the order you go in, but specifically I'm interested in, obviously we have somewhat of a family affair here, but what's your background in general, and then what led you to the field of not only radiation oncology, but applying artificial intelligence?
So we started Limbus as a project during my medical residency training in 2017. I was doing some Atlas-based projects, and I was working with Jonathan, who's my younger brother. We were working on some iOS applications, just kind of as a side project, working on some nomograms. And at one point, I kind of just threw it out there to Jonathan and Carter. You know, what's going on with this AI business? Like, could we potentially train like an AI model to do what the Atlas-based contouring wasn't good at? And so I know Carter from way back, like since kindergarten, been best friends, and I know he was out working in Toronto and had a background in machine learning. So it just happened that the only two engineers I knew and was close with were pretty much perfect to start this project on.
That's actually pretty close if one of them's your brother and one of them you've known since kindergarten.
Yeah.
And that you're making a business survive together. That's a real testament to the relationship. Josh, why don't you tell us a little bit more you specifically, and start with the basics. Let the whole world know how to correctly pronounce your last name.
Oh, Giambattista, Josh Giambattista. So I did my medical residency training in British Columbia, and I'm currently working as a full-time RO in Saskatchewan. And the AI project was kind of an area of interest. Was kind of keenly interested in contour comparisons and clinical workflow during my medical residency. And that kind of just led to a natural spin-off with working on Limbus. So currently I still oversee most of our data set management and clinical projects, and my main focus is kind of on the contour quality assurance and kind of just lending my clinical guidance in terms of the model development and kind of future projects as well.
That's great. Great introduction. Well, let's go to, let's keep it in the family. And John, why don't you introduce yourself?
Yeah, sure. Jon here, co-founder of Limbus, as we talked about, and my working title now is Director of Software. So my background, like Josh said, is in engineering. I did an undergrad in electronic systems engineering. I actually did the same undergrad program as Carter, University of Regina, up in Canada here. And prior to Limbus, I was working in the industrial controls and automation field, so kind of in the oil and gas industry in Canada. So pretty far removed from radiation oncology. But I've certainly gotten up to speed in the last 5 years working on Limbus, and kind of my day-to-day now is planning our product development cycles. I work really closely with our customers, collecting feedback from the field, which we might talk about today, and kind of using that to improve our product for every single release that we put out.
That's great. Thanks. Carter.
Yeah, like John said, electrical engineering undergrad. I studied computational neuroscience for a couple of years as well. A master's, and then worked in a couple different areas in industry, in machine learning, so ad tech, and then also like some natural language processing applications. And yeah, really came to this field solely through Josh, and like John said, kind of had to get up to speed pretty quickly, but now it's kind of old hat.
Yeah, and at the end, if we have time, we can talk more about like where you see the field of AI going beyond autoseg and beyond just other modalities to cover. I'm really interested to see what you guys are interested in or even have cooking. I got to ask this just because other people might be wondering, and also I'm interested in things like this. What's the origin of the company name?
Good question. I don't actually know like when we got the name exactly, but it means border in Latin. So just kind of seemed like a fitting name.
Finding the borders of structures. So.
Yeah.
Excellent. Okay. Hey, that's a great explanation. Well, welcome. Thanks for joining. We're going to look at some cool pictures today, look at your data against the backdrop of a population, an interesting population where it's all radiation oncologists. This particular data set, C3RO case number 3. You'll be one of 3 AI vendors being able to show your wares. So before we get into even looking and see how your software works and then looking at the results, I want to kick off with a question. You've got a challenge, obviously, showing that your robot, I mean, everyone's going to buy into robots are faster and more consistent. That's what robots do. You've got a special challenge where you have to say our robot is something compared to your humans. And the special challenge that I see is those humans might have varying opinions themselves. So if you can kind of describe what's that like working with not only customers you've got, but potential customers, what is it they're asking for? What kind of evidence do they expect to see? Or what kind of tests do they do with your software before they sign up?
That's a good question. Jon could probably explain more of the tests, but I think just as a background, we're pretty keenly aware of these differences and kind of identifying the problem of you basically have to set a different standard for each AI model based on the context of inter-observer variability. So one of our earliest studies was out of British Columbia, basically doing exactly that, like a multi-observer study where they're independently contouring scans. Then we're comparing all the manual contours to each other as if each manual contour is their own expert for that case, and then wanting to see how the AI fits within that variability. And we found out early on with good models and kind of what we had learned in terms of model training and really good data set curation that we could get models into that inter-observer variability range. And I think, from our perspective, it's publishing that in peer-reviewed research to kind of back up the credibility of where the models are at. And we kind of use that as the strength when going into clinics and discussing. And then the other aspect of things is operationally, the application's like very easy for centers to install. So we really encourage any clinics that we're working with to get an installation, install it on their own hardware, and just run scans, evaluate, or run it prospectively if they want to see how it's impacting their day-to-day workflow.
So I guess implicit in that is you'll allow people to try it before they buy it, so to speak, and basically do validation however they deem it, or do you?
Yeah. So there's certainly no standardized way to validate AI autoseg. So we kind of see. I mean, we see some patterns, and some customers kind of come to the same conclusion about how to do it. But typically, it's sometimes they'll run a quantitative analysis. They'll actually run 400 scans retrospectively and actually do dice comparisons or some other distance metrics to look at how our contours compare to theirs clinically. Sometimes clinics will just implement it prospectively immediately, and they'll realize the time savings, and that's enough for them. So it's kind of a mix between the two. But as far as how we want clinics to ideally utilize their trial with Limbus, we want them to implement it prospectively, and we want to capture quantitative and qualitative data. And for qualitative data, we push them to create surveys where they'll basically interview or have the radiation oncologist or dosimetrist or whoever is reviewing the contours grade them in terms of an editing scale. So you go from no edits to major edits, and kind of from that and the quantitative evidence, you can really get a good picture of how the AI is performing on their particular contouring practices.
Do you help guide those, or do you just say do this for every data set? Because I've got a morbid curiosity here, because the real way, an interesting way to do this would be blindly, obviously, with a mixture of human contours in there, even some of their own, and see if they grade their own as accurate. Have you dabbled in that?
Yeah, actually, I guess this past year we did a study with Nova Scotia, University of Nova Scotia in Canada, and that's exactly what we did. We designed a web kind of viewer that you could scroll through images and give grades to the different contours, and we basically randomized and blinded them. So half of the structures that they would see on the scan were human, and half the structures they'd see on the scan were AI. So there's no way to say, oh, this one kind of looks like AI, so I bet all of these are AI contours or something like that. And yeah, really interesting results. I'd say favorable towards AI solutions like our own, and those will hopefully be published this year. But yeah, it was a really cool study.
Oh, you gotta ping us or come back to this video and put it in the comment when it gets published, because I really would love to see that.
Yeah, the abstract's been submitted, so it's results should be available really soon. That's
great. Now, were those their own set, or they were just peers that they didn't know? Like, were they their own data sets that they were kind of grading their colleagues without knowing it?
Yeah, they were, and in fact, they were so reviewed clinical contours, essentially. So these were clinical contours that they had used, and then that were also reviewed again, and then we're comparing those to our AI structures. Yeah, so is their own data. So if they're making a decision about using our contours, this is a great test for them.
So that's a very neat little option to help people with validation. If they throw a bunch of data into a bucket and you allow people to reproduce this and tell them what their votes were.
Yep.
Yeah, exactly.
Yeah, there was a lot of just doing it as a research project, a lot of work going in just to make sure it was powered correctly, and there was all the scans sent over had the right structures on them. But you could do more of like an informal version of this for clinics that wanted to test. But yeah, the coolest thing that I think the coolest aspect of it is the web interface allowed the doctors to do these ratings really quickly, whereas doing it otherwise, like having to go into a treatment planning system to record these to separate database, we know radiation oncologists wouldn't have time for that. So we were actually able to generate this comparison data pretty quickly.
It's a great idea.
Credit to the engineers for that.
Yeah, it's a great idea. Did that include things like it was this long, this wide, like basic things like that are kind of macro metrics for each structure, or was it just, hey, we're showing you pictures, review it however you would review it?
Yeah, it was like a four-point scale from if you were reviewing a peer's contours and you saw these, would you make no change, or would you do a complete revision, or a major change or minor changes? So graded on that scale.
I get so interested in this, so I'm going to stay on it for one more question. Chances are, if I'm interested, other people will be. I think we're going to get kind of a niche audience here for all these conversations, but I think the people they're going to want to know more if they're watching. As you look forward to kind of refining models that you already have, I'm sure continually, is there enough, what kind of sensitivity would you need to say, if you employed that test, to figure out if the new model is really an upgrade over the other? Do you think there's a fine enough resolution in that method, or would you need kind of more of a scale? Or that might get difficult, because a 4 and a 4, they may say one is better than another, but if there's not a way to vote on it, it's a
yeah, that granularity, it would be tough to say, especially now that our models are at a place where the incremental improvements are fairly minor now that we have so much data and have gone through this process so much. So it might be hard to pick that up and use this to guide model development, but I think it's at least interesting as a the AI versus human kind of thing, and whether it makes sense to implement this in clinic.
Yeah, one more question, then we'll hop over. We got a lot of pretty pictures to look at. We want to see how your software works. Just one more. Do you see your models converging in the future, where you get more and more consensus in the field, so you have models that satisfy everyone? Or do you see there's going to be a market pull for diverging models where they have kind of unique tastes that they prefer? And would you support the latter if that was the...
My philosophy on this is, I think for most structures, it converges on like a single ground truth definition. I mean, if you look at most of the organs, the well-defined borders, and most people are contouring them how they should be. But there are like some exceptions to this, like virtual volumes, like bowel bags, and the lymph node regions is where things get really interesting. So I think with those types of volumes, there will be more options for customization in terms of what the clinics want for their practice. But we find in practice, like most of the structures clinics are happy with, and there aren't a lot of issues with differences in definition or kind of how we define the structures ourselves and how they interpret that.
Jon, did you have a comment on that? I saw you.
Yeah, I was going to say, like, where I think we'll see the divergence is, I guess, kind of geographically, based on how clinicians, what guidelines clinicians follow for contouring, and that comes back to like CTV and lymph node volumes. There's differences between RTOG and ESRO guidelines. So just based on that, if their practices aren't changing, then I think the machine learning needs to adapt to fit their needs. But like Josh said, for the organs at risk, I think the definitions are fairly standardized, globally. So I think there's less of a deviation that's needed from manufacturers.
Yeah, it's something I worry about is if we allow it to diverge. So, I mean, just for the record, in a dimming world, in a quality world, for organs at risk, for sure, there should be convergence. It challenges the field to come to an agreement on what right is. But that's why I think there's this wonderful power in these consensus studies, and I think you're about to see some of that now. It really does take out the outliers and emphasize the range of expectation, just visually and quantitatively. So before we jump into that, if one of you wants to drive and give us a quick ride in your convertible, show us what, well, first of all, I think show us what you did to produce this structure set. I provided the images to you. You had them back very quickly. If one of you wants to drive, be great. Yeah,
sure. I'll share my screen. I won't give like a full demo, but I'll run the scan and I can talk about generally how it works and what we do. So do you see my screen? You should see Limbus contour.
We see it.
Okay, great. So I have the scan here that I ran view Ben. So I just have the DICOM files in a folder. And our software is pretty simple. Like we essentially just monitor an import folder, which would typically have the CT scanner pushing to automatically. And then we send the structure sets, where they belong, which is typically some location that the treatment planning system can import from. So I just, copied the scan data into my import folder. Limbus imported it. Everything's running automatically, so it detected this was a head and neck scan. There's probably some metadata on this scan that usually I'll just have generic rules set up to detect a body part examine tag. So if that had head or neck, Limbus would have picked that up and automatically classified it with our standard head and neck template. So this thing's chugging along. It's applying contours. All this is running locally. This machine here is just kind of a desktop class workstation with an i7. So I'm running on CPU right now, and contours should be done in about a minute on any modern Intel CPU. And as far as like the structures to run and how our software works, we basically run Limbus through this templating system. So all of the structures we have available for automatic contouring are selectable, and clinicians can build templates or protocols for what structures they want to apply for each treatment site. And oftentimes we can take their treatment planning system config and automatically pull in their desired names and colors, and they really just customize this to match exactly what they would want in the treatment planning system for each of their scans. So what I ran here was just the standard head and neck template that we have included out of the box, but pretty much every customer customizes this to their needs. And yeah, that scan is already done processing, so the structure set's going to be exported to my output folder here. And as far as runtimes, pretty quick, like I said, with under a minute for how many head and neck structures we just produced.
Now,
so that's pretty much. Go ahead, Ben.
Normally in the wild, then the user would or would not have these screens up? It's happening automatically.
They wouldn't. This is really designed to like run completely in the background. So this interface is basically just for configuration, and there are cases where Limbus can't detect which template or which structures to apply automatically, and in those cases the scans kind of sit and populate in this import table. So someone would log in, select which structure or template to apply, and push the scan through. But yeah, this is designed to run without even a user being logged into the machine. So really just like intercept from CT, apply these contours, and send the structures out to the treatment planning system. So
you're also running as an SCP and an SCU to kind of kick it on to the next step in terms of DICOM?
Yeah, that's right. So the SCU and SCP aren't built into this software, but we have separate Windows services that run an SCP and SCU, and that kind of handles the data transfer. There's some treatment planning systems where you don't need DICOM networking. You can kind of just do things through the file system. So it's very simple, and there's a variety of ways to kind of get data in and out and have it work seamlessly in a clinical workflow.
So then also, I think it's obvious, Windows-based and then local installation as of now, right?
Yeah, Windows-based. We also have a Mac OS version, but not a lot of demand for that. It's kind of it's for internal use. Some clinicians test on their personal MacBooks, which is fine. And we only offer a local solution. So like I said, this is running on CPU. This particular machine also has a GPU, so contouring would be twice as fast as it was if I had that enabled. And yeah, all this just runs on the local machine. We'll interface with the clinic's network drives of their DICOM SCPs, SCUs, and that's how we push data around and contour it.
I think that's very clear. We'll get a whole list of everything your engine produced in your commercial version as of today when we take a look at it. We'll only be able to study the structures where we have the data, but it's a pretty long list. So if you wanted a quick rundown of the type of models you have now and the number of structures per, if you can go through that real quick.
Yeah, absolutely. So I'll just pull up, this screen here is kind of like the global structure settings. So it's a quick way to configure your names and colors for every single structure that we have. So each row here is basically a model that we have produced, and you'll see there's a ton in here. I think this version has over 70. Our next version will be over 100, I think. So we're adding a ton of additional abdominal structures, and we're splitting head and neck lymph nodes out. So working on a lot of things. We also have MRI structures now for a T1 contrast. These are just brain MRIs. We'll be able to scroll up the list here, and you can kind of see what our offering is in the current version. So all these structures are basically grouped into our standard templates.
I got it.
For each treatment side out of the box.
A master list, and then you have them grouped into what will automatically get run. And the user's in control of those templates, I think you said.
Yeah, absolutely. So I can go in here, and if I don't want to contour certain structures for my brain patients, then I can just remove them. And we only contour what we need, basically, and we try to match exactly what the clinicians want in their structure protocols at the treatment planning system.
Very good. Clear as day. Does anyone else have any comments on this before we dive in?
The only other option that's pretty useful sometimes is that we have like an nth slice option. So for a lot of the CTVs, we'll recommend clinicians just export them every like second or third slice. It makes it pretty quick to edit and then interpolate to come up with the final CTVs for like head and neck or pelvis.
Makes sense. All right, great. Well, we'll go ahead and switch over.
Yeah, let's do it. Yeah, it's pretty simple. We kind of designed it not to be flashy. So the flashy part is the contours. It should be.
The more and more, the best user interface is no user interface.
Exactly.
All right, here we are, ready to inspect. Just a quick, I thought it'd be cool to take a look and see. Here is the list of structures that were created by the Limbus software. If anyone's interested, looks like
right.
It's quite a few. So are you adding to this list, or do you find this is a kind of the good base list for head and neck that looks like a pretty big list? It's a pretty good
base list. Like we're gonna have mostly splitting the lymph nodes will be next phase. Other things like splitting the constrictor muscles, some other brain-related structures. But this is what most clinics use. I'd say like 95% of the time.
Excellent. All right. So, like I said, we won't be able to study all of these. The AI engines are producing more than we have data for. But I tell you what, of the list of candidates, which are in this case brainstem, left and right parotid, left and right submandibular gland, larynx, and the constrictor muscles, what would you like to start with? You're the guest. You tell me.
Let's start with brainstem.
Okay.
Sounds pretty straightforward.
Good place to start. What I'm going to do then is just load up what's the consensus grid. You'll see them as dose values. It's ISO agreement lines, viewed as dose and studied as dose. And I think for this particular case, we had about 70 radiation oncologists submit their contours. So it's a pretty good, smooth consensus. All right. What I'm going to do is flip over here. We'll go find it. There we go. We start to see it. And I'll turn all the structures off except your brainstem. And what we can do here, yeah, there we go, right in the middle. What we can do, and you can totally backseat drive if you want, but we'll kind of do a quick fly through. Mm-hmm. So here we start seeing the consensus, and I've got it now, so the minimal viewed is 10%. If you want to see the whole, the union of anyone's contours, I can turn on like 0.1%, but we'll do a quick fly through. Mm-hmm. And the big yellow line here is yours. Mm-hmm. So visually, it's falling kind of right in the middle of the band. This was one of the lesser variable structures in this particular data set.
It's good that there's not, superiorly, it's all pretty uniform within a couple slices. Looks like.
Yeah, right in there. I think there's a little bit where, yeah, but otherwise, this is a sagittal view. It's kind of a poor reconstruction. That's my fault, not Limbus' fault. And then we want to pop over to coronal. We can kind of take a look. So visually, you're right in the middle, which is kind of what you want to see.
Yep.
I put this cheap little tool in here where I can actually, so let's find the highest agreement of any ISO agreement line. So first of all, there's their dice. We'll want to focus here. Your dice is over 0.9, and there'll be another podcast where we're kind of going over experts versus consensus, experts versus AI, but definitely a dice of 0.9 starts saying very high agreement. I'm also analyzing distance of max disagreement in terms of a vector length. But it's kind of interesting here, you're kind of almost right dead set in the middle of the population, so your maximum consensus agreement was 47.2 with a very high dice. Is there anything else that's interesting to do with consensus? Like, and by the way, all of you will get all of these consensus grids, whether you use them or not, because you volunteered for the podcast. I'll send them all to you. Okay. Use them for whatever. But is there anything else you want to see or talk about on this?
I think for brainstem, it'd be interesting to see kind of like ignoring some of the inferior slices and how they're changing it, because one thing we do with brainstem is like we've developed the model so the brainstem spinal cord always have a very consistent and like nice smooth junction between. So we make sure there's like never going to be a gap between brainstem and spinal cord, and actually you'll get like a really nice contour on the lowest slice of brainstem and then the next spinal cord one. So generally for comparisons on structures like this, we'd like the experts that are contouring over the spinal cord. I think it's relatively okay in this setting, and I'd kind of want to see where the other differences are and kind of highlight those a bit more. Does that make sense?
It does. If we want to visually kind of hone in on the differences here, it's where you see these gradients splay out. So at the inferior edge is one of them, the superior edge, and then a little bit here on the back. And so, and your contour, I turned your spinal cord on there because you mentioned it, but yeah, you're right there, splitting the difference right at about 50, where 50% of the people agreed to stop. A little bit little bit of an outlier up here. Oh, that's tiny. Oops. Yeah, that's not even worth looking at. You're, a little conservative, I guess would be the word. But yeah. And yeah, when you're looking at things like max dose, that's probably conservative is the right word. Otherwise, this is probably what you would want to see. If you saw your contours falling outside a population of 70 physicians, that might be trouble, but we're seeing the opposite here. And just, for your record here, having an agreement level at 47.2 is also pretty comforting that it's not on one of the fringes. Although if it was on one of the fringes, it wouldn't necessarily be a bad thing. It might mean that there's a tendency in the population to under contour or over contour, but that doesn't mean that being on the fringe is bad, because it could be that most people are doing it wrong.
Yeah, we might see that with some of the other structures. But.
We're going to go through all of them. So this would be one of the, hopefully one with the least surprises. Why don't you pick the next one?
We go head to toe. Do parotid glands maybe?
Sure. Let's do left and then right.
Sure.
All right, we have just the consensus. I tell you what we'll do. Let's do a fly through of the consensus first.
I could predict where the contours are going to be, just based on how I kind of know how the models behave.
All right.
But here, I think you'll definitely see it trending more towards the outliers that tend to be a bit more generous. But I think parotid's like structure that's under contoured a lot in practice.
Well, let's test your theory. And by the way, that's why I think you'll be really interested when we show your results versus the experts, because I can tell you, or you can watch the video there too, just visually inspection of the experts. I think all four of them did basically contoured the way you just described. So let's turn yours on. It'll be a peach color. Yep, there we go. So it's definitely going into the lower agreement, meaning I said lower ISO agreement, which means kind of a more conservative approach in general. Otherwise, your contour is really smooth. That's one thing I love about the AI and even consensus. It tends to be very smooth and not jittery and blocky like we sometimes see in the real world. Now, there's a little interesting artifact. One little artifact
I think it's probably picking up a bit of the parotid lobe there. If we can look on the CT, it might be hard to see on this setting, or it might either that or it just thinks it's it thinks it's picking up a piece there.
It's just a tiny little piece. Other than that, looks very, very smooth. Let's look in the other view, see if we see anything. And if you see anything specifically you want to see, let me know. Let's go to this coronal. And again, nobody take these reconstructions. Don't hold those against Limbus. That's just my bad reconstruction software. So it looked, and so here, but again, we see it's inside the envelope, which is a good thing, and it tends to be kind of in the middle. So if you had to guess on an ISO agreement line of your max dice, what would you all guess?
So that's like the dice with the whole population?
If basically go through all the ISO agreement lines, think of it like an isodose line, an ISO agreement. Your last one was 47.2. So an example here would be if you had a person or an engine that matched with a really high ISO agreement, it means it was much smaller. It was tending to be very small and not including many of the voxels. Whereas if it's a lower number, you're drawing it larger. You're drawing it with the people who agree that the structure should be larger, if that makes sense.
Yeah. Probably within like 20 to 30.
Let's see.
Maybe.
40.9.
40. Well.
But, oh, wow. So this is one of the biggest dice, 0.933. So at the, let's call it 41% agreement, which is still pretty close. Your last one was 47.2. You are getting a high degree of overlap, which again, I think that should be pretty comforting. Because I think studying these consensus, it does smooth out where differences in opinion lie. Let's see if we get similar results with the right parotid there. So let's switch over there. We'll turn your structure on, and I'll change the grid.
This is really cool.
Yeah, the numbers I'm crunching for kind of the final wrap up are, you know, these charts are super interesting, and I can already tell you there are some very interesting findings. I almost don't want to bust it here, other than to say so far, well, it's not really a surprise, but robust consensus and AI tend to be most robust with threading the needle of agreeing with experts, where experts have, so one expert versus another, they may not match very well, but when you put a bunch of experts together, they start to look like the consensus, which is intuitive, what you might expect. So here we have, it's a little hard to see, but you got a blue line here, and we'll go, we're looking, let's look at the axials. Yeah, so qualitatively, looks very similar. Actually, on this one, you start right on the same slice as when the majority of people started. Must be some pretty good contrast over here. If you want to take a look at that real quick. I probably don't have the best window level. I'm sorry. Did you find anything remarkable about this image set, by the way, John, when you ran it? Pretty run-of-the-mill?
Yeah, pretty run-of-the-mill. A lot of dental artifact,
Yeah.
Which you might see in some of the other structures, but yeah, pretty standard looking head and neck CT.
And I think the AI is like a bit less confident on like higher quality scans. It tends to do a bit better on the smaller lobes and the deeper parotid. Just kind of depending on the scan quality, it could be hard for the AI. Like it won't tend to contour as deep.
Right. Now, here we saw this before. We saw this on the other side only for one slice. So tell us what might be going on here. Actually, what I'll do is
I think there's actually probably some parotid tissue there, and it's typically not contoured. I'd like to see what the experts contoured on that one, because that would be interesting to look at.
So here, actually, this is the first we've seen. So this is kind of this is the union of everyone. So no one went up here. Largely, you're kind of dead in the middle of the wisdom of the crowd, with just the exception of this little wing up here. So that's an interesting thing to look at. Let's find out. We had a 0.933, a very high agreement with a level of the crowd. Let's see if we have that over here as well. Yeah, 928. These numbers are very high, and kind of at the same. I mean, we're splitting hairs. I think the last one was 41. This is 43. So there's a level there where you're just a little more conservative than the absolute median of a collection of 70 rad-oncs is a way I might say that. Cool. No, you guys feel good about that?
Yeah.
Yeah, I think.
Yeah.
I think that's the kind
I'd
of thing
definitely
we'll
like
see.
to see how it compares to the experts. That would be very interesting.
You will. It's just we want to focus just on your contours. Realize there, of course, though, when experts disagree with each other, AI can't hit all of them.
Yeah.
But it's amazing. You'll see in that consensus starts to agree with all of them better than any of them agree with each other. And the same trend so far I'm starting to see with the AI. I'm not done with the numbers, but those will all be kind of in a summary podcast I'll do hopefully at the same time that I release all these. Let's do, while we're on this side of the patient, let's do the submandibular. Now this one could be interesting because this, I think, this was the side of the GTV. So there's a lot going on over here. Yeah, I think when I looked at the experts here, they agreed much higher on the left submandibular gland than they did on the right, and I think that's because it's just a little more challenging. It's a little less standard. So here we go with the population, and then we start to see yours come in here. We do a little optimization here. Well, actually, before we even go and look at yours, so there's a lot of variation in the population of physicians here with that big tail. And you're, again, right in the middle of it. So that's, so we're going down. A lot of agreement down here. Those tight data gradients, that's nirvana right there. We start to see as we go superior, there starts to spread out and be more disagreement. So any comments or anything you want to see on the right parotid here? Let's look at the coronal. Again, there's yours.
Just like in terms of having the models adapt to, like on that side, you have a large involved lymph node, and it's displacing the gland compared to the other side. It's actually somewhat difficult to get the models to behave that way. Like you have to ensure they're trained on a lot of good submandibular glands that are actually contoured correctly on the disease side, which in practice doesn't always happen. Like sometimes if you know certain structure is gonna kind of get max dose and go over tolerance, you might not contour it as accurately. So I kind of just saying there can be pitfalls to using just clinical data. Like we had to make sure we reviewed a lot of
for sure.
submandibular glands, all of them going into our training data. But
so with a high level of variation in the population, you seem to be, again, right there in the median. So let's see mathematically how close we are. Wow. So 0.907, and you're, all of them have been kind of in that 40 to 50 range. That's weird. If someone were to have a hypothesis, that would probably be the hypothesis. And so far it's pretty consistent. Again, a lower, what I like personally to see is high numbers here, because it means we can glean something from the consensus that's very useful as a robust standard. That's kind of what I'm interested in. And I think, hopefully as we generate more and more consensus, companies like yours can throw it into your validation suite. Why not? So we got a 0.9, a 50. Let's see if those numbers change over on the left. Do you have any predictions?
I think it'll probably be about the same.
I predict it'll be even higher.
Yeah.
Just because of what you said, it's a little more normal looking over here.
Yeah.
But we shall see. So we're at the left submandibular gland. Well, clearly there's less variation in the population. So outside of even what yours is.
Yeah, for sure.
Yeah, that's a friendlier looking consensus. And then we toggle yours on, kind of go through the sagittal, or I'm in coronal here. Very, very reasonable again. Here we're, with the more conservative opinions in the crowd. And let's do bottom to top. Boy, it's with the green, with the 50% being green and your contour being green. Let me actually change the opacity a little bit. There, it stands out a little better. Yeah, wow. So I'm going to stick with my prediction of a high dice. Anybody?
Yeah, I think you're right.
Yeah, it's right around the same. And again, though, right around 50%. I wonder where there's a little, because I mean, qualitatively, it looks right where you'd expect it to be. But again, 0.9 is high. By the way, let me take a little aside here. Tell me if someone has done this already. It's been a few years since I was coming up with new metrics for this, but the more I do it, the more I want to come up with a modified dice. So the problem with dice is you may overlap, but when you don't overlap, it doesn't tell you how extreme it is. Okay, so you add in the max distance. Well, that's too sensitive. I almost want to do a modified dice where it says, give it a tolerance of so many millimeters and include that in the intersection. Do you see people doing that, or do you do that on your own? In other words, it counts as intersection if you are intersecting or within like 3 millimeters or something like that.
Yeah, that makes sense. I think we pretty much just use standard dice, and I think a lot of the papers on this stuff are also kind of falling back on dice. But yeah, I think there's definitely room for better metrics for sure.
Yeah, with the
95.
Go ahead.
Like we use the 95% Hausdorff distance, but it's not the exact same as what you're describing.
Yeah, no, that's a good one too. It kind of removes the outliers, but tells you where most things are. I just know that dice, I don't, even though we're showing dice here, that's just because everybody uses it. I don't like it because you can be off by 1 millimeter and you're counting the same as if you're off by 20 millimeters. Then I did the structure metric, which is really the most sensitive metric out there because the farther you away, the more penalty is levied. But it's so sensitive that it freaks people out. You can play with the penalty function as you get farther away, but it's so sensitive. It does tend to fall off a cliff when you get. I really like it, but I'm a little biased. But we're not looking at that here. We're just looking at the dice. So now we're going to get into gets a little more interesting here. We've got 2 structures left. The 2 highest variation structures when we look at the population. So we'll look at the larynx first.
Larynx is going to be a disaster in terms of like the amount of variation.
Well, I think it'll be a great chance for you to kind of comment on what is the larynx, because whatever the instructions were given to 70 radiation oncologists, as you'll see, either the instructions weren't explicit enough, either by design or by accident, or people just have different opinions still. So this is population only. And you just see it's nothing but variation. Like the region, the more blooming it is, the more people. So before we toggle yours on, what are some of the challenges of this particular structure? Do you look for particular types of data when you train your models, obviously?
Well, this is like a perfect example for just a lot of variation in practice. And so for something like this, I think for our data sets, we basically just went through and for the most part just recontoured all of them because I find with that amount of variation, it's better to just control the data up front, and then we have a better idea what the model output's going to be. And the downside is we kind of have to come up with a definition we like and provide that as the option. But it's not feasible to train when you have this much of a variation. The models are going to be confused, basically. Right. You have to tell the models what is the definition of larynx.
And this would be one of those structures where, let's say you deliver it to a potential customer and they say, well, it doesn't match what I produce. Like, what's your diplomatic response to something like that?
Ours is based on DeHanka, like we're just taking the subregions and that's kind of what the larynx output is right now. But I mean, there's like general anatomic definitions of like what supraglottic larynx is and what larynx is. But clinics haven't had a lot of feedback on this one in particular. So it's a good question. I'm not sure if they just, clinics might just start using our larynx and they might just be happy with it. We haven't had a lot of opinionated clinics on larynx right now. But I know there are some variations in how it's contoured.
Well, here's yours. Nice contrast with the magenta over. This is a case where the sagittal, it will highlight. So a lot of the population did go a good bit more superior than you did. This is the first time we've seen that with your data. So you might kind of qualitatively explain why might this happen.
We just were very specific in our training data about where the superior slice should be, and we're like very close to the atlas on it. So yeah, it makes sense that it's not contouring into like the supraglottic larynx, and that was just kind of a design choice. But the models are very consistent there. You get very similar results if you run it on 100 scans. And then inferiorly, we're not doing much in terms of post-processing yet. Like once we have our cricoid, we'll be able to set the inferior boundary. So it did run a couple slices too low on this one, I think.
Well, what's interesting here, we're kind of now seeing the numbers back up what you said. First of all, this is still a very high dice, but notice how the number's not here 40 to 50. It's almost 70, which is consistent with you are still, for such a highly variable structure, you're still in a high agreement with the population, but with a different level of the population. So I'm real curious to know, because as simple-minded as I am, I kind of have this dream that if you get enough radiation oncologist data to do a consensus, then we can drive towards gold standards that have different ISO agreement lines, probably levels that we're looking at. I don't think we can just say 50% across the board, because it all depends on today versus maybe the ground truth. Are people under contouring, over contouring? Well, I think it's both, and it depends on the structure.
Totally, yeah.
Still a high agreement, 844 for such a variation.
Yeah, that's surprising.
For example, here, I think this was one of the structures. If you go back and watch, because I did this exercise for experts versus consensus. I think I didn't have time to go through all these numbers, but some of them of experts versus a consensus, I mean, they were getting 0.3, 0.4 dice max. And that's when you start to say, whoa, we got a lot of work to do. So I'm very encouraged by this. That's cool. And I think here, we'll end with the whopper. That would be the constrictor muscles.
I think this will compare, I think it'll actually compare fairly to the distribution here, but we'll see. One tricky thing is the gross tumor volume on this one. It's kind of right within where the constrictor muscle is, so I'm not sure how that will affect results.
Well, this one definitely had big variation. It's kind of interesting when you look at, this is the population consensus here. When you look at it, you're like, hey, everyone was kind of in the same neighborhood, which is great.
Yeah.
That is good. But they didn't overlap. They're all in the same neighborhood. So it's almost like that kind of precision versus accuracy argument that we all learned when we were in grade school. Let's take a look here. And again, we'll start at, this is the consensus, and then we'll go back through and look at yours before I turn yours on. So you can kind of soak this up. By the way, if you really want to see something interesting here, let me add the whole union. So let me add a small, like a minimal, one or more people type of thing. And then you start to see, okay.
Oh my God, yeah.
All right, now we will turn on the Limbus constrictor muscles, which are, here we go. And we'll start going inferior. We don't see the Limbus contour. Here we go. So good overlap with the cloud.
Yeah. Where the tumor is, you'll see the Limbus contour will still contour on that side. That's by design.
Got it. Okay,
Yeah.
I'm glad you pointed that out. That's, other people stopped. You're basically saying that muscle's still there.
Yeah, and yeah, I mean, if the radiation oncologists are seeing a tumor there, they're probably not going to contour the OAR over it. So the model's still trying to, basically still trying to contour there.
Makes sense. Yeah, there you see the clear asymmetry in the population, but you made yours symmetric. You know, I guess that's one of the things too. You probably have to, in some cases, you probably have to say, this is how we do it, and you just be transparent about it. And if people say, okay, well, we'll take that as a starting point and do some edits. Do you see that happen a lot?
Yeah, it depends on the region. With CTVs, it's definitely more opinionated in terms of oncologists being willing to start with it versus not. Like if they're very used to following a certain guideline, Sometimes that's like very important for them. But with most of the organs at risk, like they seem to be pretty willing to use these as a starting point, and happy with the consistency.
So really, it was just as we get to the top is where we start to just see differences in the population. But otherwise, there's well, you know what though? I have to be careful when I say there's agreement in the population, because you see no red. No red means maybe the highest agreement here might be 70%. So the people who did contour here contoured in the same place, but a lot of people didn't contour here, if that makes sense. Let's do our little
and
magic.
We've designed the constrictors to connect right to the upper esophagus, so it probably will run a little bit lower than the population.
Well, I tell you, looks to me like you're right with, again, the median of okay, a little lower. Okay, good point.
A little bit, couple slices.
Slices.
That's kind of by design. Yeah.
Good. All right, let's see. Wow, okay, so I'm really surprised. Now there's two interesting things here. First, I'm surprised the max dice is so high, because this is a small flat structure. You can have a low dice even though you're kind of in the vicinity. But the other interesting thing here is you're definitely contouring more. So you have a high agreement with the union of 81% of the people who contoured. I may not have said that perfectly right, but this number's a lot lower. So when you're agreeing with a lot lower, you're contouring more and more voxels, but still equal to what 20% or more of the physicians would agree. So really neat stuff. Wow, okay. This was, maybe I'm easy to please, but this was a lot of fun here. Have you, just a couple closing questions. First of all, thanks again for your time. I hope you saw some cool stuff. Definitely, it was neat to see your contours agreeing well with the population. That's gotta feel good for you, for a few structures that were actually had high variation. Let's see, just a couple closing questions. Do you see? One is more philosophical. Do you think it would be a good thing for all the clinical trials data we have ever done to have auto contouring run back through all of it, just to get and then to analyze the new DVH data? Because otherwise, I think we have a lot of contouring variation built into these clinical trials, and when we're looking at DVH points as if it's law. As a radiation oncologist, what's your opinion on that?
Yeah, that's a really interesting question. Yeah, I think so. I think that would be really interesting. And I mean, you can implement something like that and have a second check. So you could like run on a huge retrospective data set, look at the outlying dice scores, and then just take a look and see, is that major human variation there, obviously human error that got through the quality assurance process, or is that an AI model error on that scan? More often than not, you'll see like those variations in manual contouring at this point. You might find some AI errors, but I find our models are pretty robust unless there's some major outlier in patient positioning or something like that. But you could do it like a pretty sensible way like that, and if 70% of the scans have like very high dice agreement, then those ones are probably good to use for those analysis.
Well, I appreciate your sensible approach. I have a very aggressive approach that I would love to see for any clinical trials data where there are actually correlations done, predictive values assessed for DVH points that are taken as law. I would love to see, especially if you have multiple AI models, as many as you want, run them all against the image sets to produce, let's just start with organs at risk. To produce the organs at risk, calculate the new DVHs, the new DVH points that were run in the correlation, which AI engine produces structures that have the highest predictive value of the DVH. You see, if you're looking at things like max or dose to a small volume, or min, or a dose to all the volume but a small volume, it's going to be very sensitive to errors even on the millimeter scale. And I think if you have an AI engine, you could go and say, hey, this thing that didn't look predictive before, now it is, or this thing that was predictive with a maybe medium correlation might become very strong. But then you may have and that's that would be a really neat way to pick which AI is best, because that's the AI that's going to produce plans that will produce doses that have best outcome.
That's a good point. Yeah. I never really thought of it that way, and I think
I'm going to die on that hill, man.
Yeah,
that's part of why I'm.
The threshold will be a lot different depending on the structure and depending on the situation. But yeah, I think that is. I think in those clinical trials you would see a lot of variation. Probably, they have to on these trials, like they have to get these patients onto treatment, and there's always a time crunch, and so things can't be done perfectly. But in practice, if you can show it having value in that retrospective, it makes sense also to implement it like prospectively. So trials are all starting from like a very similar starting point, and even potentially having AI or a secondary AI to do quality assurance checks in the trials.
Yeah, so technically the proposal there isn't an AI-specific proposal. It's more of a retrospective contouring. What contours really go with the dose that produces the DVHs that are most predictive? AI just makes it so that it can be automated. So now you can run through tranches and tranches of data and just automatically calculate and say, what did we learn? I love this prospect. I hope someday it starts happening, because then you, obviously prospective, you're gaining all the dividends from that. And so if there's, I think you guys should go and maybe all the AI vendors maybe offer their wares to these clinical trials groups to as retrospective studies. I would love to see what comes out of it, but that's me yapping too much. Closing comments from any of you. Thanks again for attending.
That was really, really great, Ben. Thank you. Hope I didn't derail things too much, but I think it's all really interesting discussion. And hope we can participate in more of these. I think there's lots of interesting angles this type of thing can take.
You guys have a little bit of an interesting situation where the founders are radiation oncologists. So as you explained in your origin story, that's got to be a pretty nice thing where you can just pick up the phone and ask a clinical opinion. Well, what's next for Limbus? More models for AutoSeg, more modalities, or are you actually looking into other ways to apply AI?
That's a good question. I think there's still have a work to do on completing our library. So we really want to make sure our structures are quality before releasing them. So there's a lot of quality assurance that goes to the back end. Some structures are being tested in various clinical studies or prospective studies. So we want to make sure we're getting those out, and splitting the lymph nodes, and providing a few different options for lymph nodes and other structures. So that's kind of all within the core application. But I think the interesting stuff is getting into MRI and cone beam CT and adaptive. That's where we are putting a lot of resources and interest in, and comes together really interesting with like contour-based deformable fusion. It kind of opens the door to new things potentially. So
yeah. Jon, Carter, are you guys still having fun? It's I guess you're well along past the startup phase now. You're years into it. Is it just as fun as it was in the beginning?
Yeah, it's definitely fun. Still, product kind of is growing every week, and there's always new things to work on, and just no shortage of feedback now from customers too, which is great. So before we're kind of developing this in the dark, and before you have before clinics are running thousands of scans every month, you're not getting that kind of feedback. But now, as we're like distributing globally, and as we have all these thousands of scans running through Limbus, we're starting to really see like where those edge cases are and where we can put our development time into making the product better. So Carter said, like, we're kind of at the point with these models where there's diminishing returns, but we still think there's ways to improve, and we'll kind of strive until we get there, I think.
Yeah, a lot of kind of, at this point when we have all the low-hanging fruit picked off, it's kind of more challenging problems, and so there's still no shortage of cool things to be working on.
Well, it's great. It looks awesome. And Jon, Carter, and Josh, appreciate your time. And, see you at the next data set, right?
Yeah, sounds good. Yeah, thanks, Ben.
Thanks, man.
Thanks, Ben.